So let's do scattering states. Let me copy this thing. So it is still a potential well, but now I want to put the energy here. Good. Now we are experienced, right? We can write the solutions. Let me call this side A e to the I kx plus B e to the I kx. Like if you have any doubt, right? You know what to do. You write the Schrödinger equation, you look at the coefficient of the sign, and you decide if it's like decaying solutions or e to the ik or e to the minus ik form solutions. Yes?
Are you supposed to write minus ikx to 1?
Oh, yes, absolutely. Thank you. So let me write this minus. Yes, thank you. And what is k? Here, k is given by energy. So h bar squared, k squared over 2m is equal to E. Here I have, how did I choose? Let me choose C sine qx plus D cosine qx, and q is given by h bar squared q squared over 2m is equal to, now I have E naught and I have this V naught, and they add. Now, sorry, E naught, there is no E naught, E plus V naught. Good, E is positive, V naught is positive, this entire thing is positive. And similarly here, I have A, B, C, D, skip E, I have F, e to the I, kx, plus G, e to the minus I kx. Good. And now, okay, what is this? We have, you can see A, B, C, D, F, G, almost entire alphabet in our hands. And we also have E and Q, right? So if you want, we can meditate for a couple of minutes, think about good things, and then start. And this problem is a little bit different from other problems, right? Here, the scattering problem is formulated in a different way. What was the formulation? We say that we sent current from minus infinity, we sent the electrons from one side, and we put the detector on the other side. That's the setup, right? We had to change the way we look at this problem. And in that case, this A is right moving wave, this wave is left moving wave. And here I look at this is right moving, this is left moving. If I send waves from here, whatever scatters comes back, whatever transmits, but there should be nothing going left on the right side of the barrier, right? So that's why we kill this term and we make our life a little easier. Good. Also for this problem, unfortunately, there is no this even and odd separation, because we already break the symmetry by choosing to send the current from this side. Right? We cannot say, I'll take this one or this one, because that symmetry is broken by our initial conditions. Yes? So here, there was like a complicated set of equations, right, here. And what we said is like, we can separate solutions into two classes, even and odd. And whatever happens in the left side also happens on the right side. That was Yes, it was symmetric, and we use this symmetry to divide the solutions into two classes so that we don't have to have horrible looking sines and cosines in one equation. And thanks to this, you look, in one line we solve the equation. But here we cannot do that because we are saying we are sending the current from this side, then this side and this side is not symmetric anymore, right? We chose it to be broken. Okay, let's now write the boundary conditions and look how bad they are. And then we can think about, and if you don't want me to calculate, I can just write you the result and we can talk about it. Let me know, but at least let me write the boundary conditions. So we have psi continuous at minus a, right? Psi should be continuous here, and from here I have a e to the minus ika plus b e to the ika should be equal to minus c, right? There is like a minus here, I already put it outside. Minus sine qa plus d cosine qa. And cosine minus is cosine plus, so I use that symmetry. Now psi prime should be continuous at minus a, and if I take the derivative, you can see there's like ik, open the parentheses, and the same thing, exactly the same factor, but because this derivative is going to bring like a minus here, I'm going to put a minus here. And this thing is sine c q cosine minus is plus qa, and derivative of cosine is minus sine, but there will be a minus here. That minus is going to be compensated, so this is dq sine qa. Okay. Now I will do the same thing for psi continuous at a. This one is a little bit more friendly because I have only one term here, so this is going to be, let me just copy this. So this thing, I'll put a here, I'll put a here is equal to f e to the I ka. Yes. So now I am using this boundary condition, right? I am putting plus a now. Yes, this right hand side, and that's why I have inside the well I have c this thing. Oh yes. No, I think this is correct. This one? This one is minus. Look, so derivative of this is cosine, right? This one. Oh yes. So this is minus. No, this is correct. I think this is correct. Right? Let me check. I think this seems to be correct. And this is c cosine qa. And I think this is correct. But like I said, we have to keep an open mind. I always miss signs. We can come back and fix it. So psi prime continuous at a. So this is going to be q c cosine qa minus, okay, let me write it like this. The derivative of cosine is minus sine, so this is sine qa is equal to ik f e to the I k a. Good. Now let me number these equations. So this is equation number 1, this is equation number 2, this is equation number 3, and this is equation number 4. Good. And what I want to do now is, okay, so this ik, I want to cross it here, and I want to write it like this. So this, let me also take this q outside. So this is q, and this one, and this one. Let me save this notebook. So this is q. Now this thing I have is written here, ik. And similarly, I want to cross this q and write it here. So now I see these two, right? If I sum these, I eliminate b, and I have one less thing to worry about. So let's sum these two. 1 plus 2 gives. So this term cancelled. So this is 2a e to the minus ika is equal to, now I'll combine c coefficients. So c minus sine qa plus q over ik cosine qa. And I need to write d coefficients. D is like d cosine, right, plus q over ik sine. So plus d, so this one is cosine qa plus q over ik sine qa. Okay, a little longer equation, but they'll all combine in one package. Let's keep our faith. Any questions? So that's my first move. Second move, you can see I have c times sine, d times cosine, c times cosine, d times sine. So if I multiply this equation with cosine, and if I multiply this equation with sine and take the difference, I'll have something d. If I multiply this equation with sine, multiply this one with cosine and sum, I have something for c. Right? That's what I'm going to do. So this is, I'll do sine, let me write it. I'll do sine qa times 3 plus cosine qa times 4. Now this is what I'm doing, and let's see what this gives. So let me write 3 first and multiply with this thing, and I think this one will work. Erase this, erase that. So I will multiply with sine, so this is going to be sine squared, and I'll open a little bit room here. This is sine qa, and the second one is multiplied with cosine, so this is cosine squared, And so this d is d cosine qa. And I need to do the same thing here, so this is sine qa, so this is cosine qa. Good. Now if I sum these two, this one is going to kill this one. Sine squared plus cosine squared is 1, and I have an equation for c, and c is going to be equal to, so this factor sine qa plus I k over q cosine qa. Good. So I eliminated b, I have an expression for c, and if I do exactly the same thing here, the other way, I will also have something for d, and then I will substitute c here and d here, and I will have something between a and f. You can see this is something f. Good. So let me do this one more time. Can I? Okay. So this one. So what now I will do is my last move, and then I will combine everything. Do cosine qa times 3 minus sine qa times 4. And this is 3, and let me also write 4. Let me erase this. So now, okay, push these guys. Multiply this with cosine, so there is like cosine qa, and this is cosine squared. Multiply this with sine, so this is sine qa, and this is sine squared. And now I need to multiply cosine qa here, and I need to multiply sine qa here. And I take the difference. Now I have d is equal to this thing, and this is cosine qa plus ik over q sine qa. Okay, all variables are eliminated. Now I'll write them together, and you'll see there's like a very satisfying cancellation. And then that will be the end of the calculation. So let's write this thing. So this thing. Let me write it in a new page. So for sine, let's simplify, right? There are too many things to look. So this is S, this is C minus S plus this thing. Cancel this clutter. So this is C and this is S. And what is C? There's like uppercase C if you want. And now I'll write uppercase C from here. This thing. Let me write here. So let me say S plus C and this C I can erase and put this vector here. Actually, let me also push this like this. Something like that. You can see this F e to the ik minus S plus C, S plus C. Now I will do the same thing for D. So this is my D. Yes. The equation for A?
Yes, isn't that minus -2 or -k?
So this one?
No, B equals,
This one?
yes, inside the parentheses, shouldn't that be minus -k?
So let me check. I think this one I'm pretty sure correct because I did it a couple of times. So this is f e to the ik cosine. Yes, this one is minus, right?
Yes.
Yes, I appreciate. That's correct. And this minus, that means, okay, let me copy this. So this is C minus S and this is F. So okay, now I'm trying to write this vector. So D will go and I will write this guy times, open up this a little bit, this guy. Okay, let me write it. C minus ik over qs and C plus q over iks. Okay, clean everything. Okay, let's see if I can pull this off. Let me also check one more time. So this is, so minus sine plus q over ik. See, this is correct. This is sine plus ik over q. This is correct. This one is c minus iq sine, correct. I think this seems to be correct. So what I'll do is I'll cancel this and I'll put here minus 2 ik. So I have one less thing here. And I want to multiply it with 1 over f. So I have this. You can see not as bad, right? There is no arbitrary factors anymore. And this thing, now I'll open up minus s squared minus ik over q sc. Now this and this plus q over ik sc, and lastly this factor is going to be c squared plus c squared plus q over ik sc minus ik over q, this one and this one, sc, and this one and this one is minus s squared. And this is equal to, I have minus s squared minus 2s squared, c squared, I have 2 cosine squared, right? 2 cosine squared qa minus 2 sine squared qa, and I can combine these two and write it like this. So I can do it 2 times cosine 2qa. Now this guy, this guy, this guy, and this guy are taken care. And you can, this is sine times cosine, all of them, and I can write it like 1 over 2 sine 2qa, and I have what? I have minus ik over q, and there's 2, right? So let me write like a 2 here. 2 minus ik over q plus q over ik. Good. And this thing is going to be, okay, I times minus I is 1, so this is k squared plus q squared divided by I, K, Q. Now I'll erase this and write this expression. Let me check. Q squared plus K squared. Yes, I think that's correct. So let me erase this. So cancel this, cancel that. Let me take back. I think this 2 is not here. I think this 2 is a mistake. Okay, I think this Q squared minus sine squared, this one is correct. This one is correct. And this is 1/2 sine. I think this is correct. Okay. Good. Now what is this? This is 2 times A over F. And if I take the absolute value, this is going to be transmission coefficient, right? Like T inverse is equal to A over F squared. We are going to take absolute value squared. That means I have 4 here, 4 T inverse, and e to the I term, when you take the absolute value, is gone. And here I have, you can see, a real part plus imaginary part, and the way we take absolute value is real part squared. Why do I have this? Let me take back. I think I have something missing. So this is 2A. I think this is correct. This is 2SC. I think here. I think I know what's going on. So this. Okay, let's fix it. I have minus S squared minus 2S squared, 2 cosine squared. This is correct. I think this one is correct. And this one is, let me rewrite this thing one more time. So this is SC, and there is 2 of them. And there is Q over IK plus, minus IK over Q. So this is correct. And this, I think these two, and these two I'll cancel. Actually, let me do it with a different color. So this will cancel. And this thing is going to be 1/2 sine 2QA. Then when I take the absolute value, there's no 4 here. And here I'll have cosine squared 2QA plus 1 over 4 K squared plus Q squared over K squared Q squared times sine squared 2QA. And I think this is correct result. Good. Any questions? Okay, I think we are in good time. Maybe I have 10 more minutes to finish, and then we can call it a day. This is what I want to do is like, okay, let me do one more hit. So this is 1 minus sine squared 2QA. Now I can combine this one, right? This is 1 plus this thing plus, so this thing minus 1 sine squared QA. Now I have one less sine, and this thing, right, I can write this like this is k squared. Oh, by the way, I think I forgot to take the square of this thing. So this thing is squared. This thing is squared. Now I have k squared plus q squared minus plus 2k squared q squared minus 4k squared q squared, but this thing is equal to k squared minus q squared squared. Then I can combine this. Yes, yes. No, I think, oh yes, this one is 4. This one is 4. This is q squared. I think this is correct, right? Okay. So this is 1 plus 1 over 4 k squared minus q squared divided by, okay, this is squared k squared q squared. So this is sine squared QA. Good. And I think that's the final result. No more manipulation. After that, we need to put this in a form so that we can plot. So what we need to do is now we put, right, we need to, K and Q are a little bit cryptic. We want to write it in terms of energy so that we know which energy we are sending in, and we want to see how much is transmitted, how much is reflected. So for that, what I will do is, so this, remind you, h bar squared k squared over 2m is E, and h bar squared, yes?
John, can you go up a bit?
Yes.
I didn't understand how we move from sine squared to QA to sine squared to QA.
So this line, you are fine, right? This line?
Yes.
So what I did is, like I said, cosine squared is 1 minus sine squared.
Yes.
And I combine this sine squared here. There's like sine squared here, sine squared here. The coefficient here is 1. There's the coefficient here is as it is. And I have minus here. And this minus is this minus.
Okay, isn't it supposed to be then sine squared 2QA?
Oh, yes, yes, correct. Good job. Thank you. So this is 2QA. I appreciate it. Thank you. And this one is also 2QA. So h bar squared q squared over 2m is equal to E plus V naught. Good. Now let's look at this factor. So this guy is going to be E, right? There will be E here. I can multiply both numerator and denominator with h bar squared over 2m with any power of it and move things around to find this is E minus V naught. Did I get that? So this is, yes, I think this is correct. Squared divided by k squared is going to be E, and q squared is going to be E plus V naught. Cancel this. And if you divide both numerator and denominator with V naught, this is going to be epsilon plus 1, where epsilon is E over V naught. Good. Okay, this horrible looking thing turned out to be very nice and simple. And let me do the same thing with 2 times QA. 2 times QA is equal to, how did I do this? 2a, 2m over h bar squared, E plus V naught. And I want to move V naught outside, so and push 2m inside, and I can write this like this. So this is V naught divided by h bar squared over 2m 2a squared. You can see what I called quantum energy also appeared here, and inside I have epsilon plus 1. And this thing I want to call this, if you want, so I want to call this gamma, and this entire equation is going to be gamma times epsilon plus 1. And at the end, we don't have something as terrible. So this T inverse is equal to 1 plus 1 over 4. I have this vector, and I have sine squared gamma root epsilon plus 1. And now I can sketch this, right? I can choose gamma and look at the transmission as a function of energy, and that's it. Good? Let me check if I missed anything. I think this seems to be correct, but let's sketch and see. So I want to now define something T inverse, which is going to be a function of energy, and this potential valve is going to be equal to 1 plus 1 over 4, 1 over epsilon minus 1, and this is sine squared, and inside I have gamma times E. Is that correct? E plus 1, sorry.
It's supposed to be epsilon plus 1.
Oh yes, this one is plus 1, right? Yes. So this is epsilon plus 1. It is showing blue for some reason, but let's see. And I want to do plot 1 over T inverse, right? I wrote T inverse here, and I need to plot 1 over that to see the transmission. Let's put for gamma 0.1 and see 0 to, I don't know, 5. Okay, good. It seems to be working. So I want to put plot range full, and let's see how this changes with the barrier. So put manipulates, and I'll put gamma here, and comma, I don't know, 0 to, let's not make it 0, 0.01 to 10. Good. Now we have something we can play with. So this is now, there is no barrier. You can see everything is transmitted. And now I increase the barrier. You can see the transmission is like here, something less than 1. And 1 means, right, like as you, like, and so this side is energy, this side is transmission coefficient, and transmission coefficient can be 1 largest. And now I increase the barrier, and for large barriers, I think this is a little bit too much. Let me do it like 3. Okay. And here is some transmission less than 1, And high energies, you have almost perfect transmission. And as you increase, you can see something is happening here, right? Here, energy is low, but I still have a perfect transmission. Actually, let me do this. Let's plot one where perfect transmission is there. Okay, and let me also increase the energy. Let's do this 10. I increase, and blue line is converging to orange line, and at some point something happens, right? Even though I am not infinitely high energy, I have like a perfect transmission, and then it decreases, and then it starts increasing again. I increase it a little bit, and now it seems like I have two of these. I have like transmission, less transmission, full transmission, less transmission, and full transmission, right? And I increase it a little bit more. You can see now I have 1, 2, 3, 4 of these, right? And what these are, okay, let me. So this is our energy, this is our transmission, and you can see here is perfect transmission. I think there's another one maybe here, and these are what we call resonance, right? And we can calculate what when we have perfect resonance, because so this is inverse T, and whenever I have this factor 0, I have perfect transmission. And this factor is 0 whenever this sign is 0. And when is sign 0? Sign is 0 when this gamma times epsilon plus 1 is something like n times pi. Right? Whenever I have this condition, even if my energy is not infinitely high, I transmit because I resonate with the valve. And if you manipulate this, okay, let me find. So what you find from here is En h bar squared over 2m 2a squared n squared pi squared minus v naught. So what is happening is you have this valve, and if you want, there is like trace of these box energies, right? This is like energy for like infinite box, and this like your energy is up high somewhere like here, but you still see the trace of these bound states if you want bound state. And what this means is like you are sending a wave and it reflects from here, comes back, and it reflects from there and then transmits. And if the wavelength is perfectly matching the width of the valve, if that's happening, what happens is like something like this, for example. There is no reflection because you resonate with the valve. Or if you are like this, again, you resonate with the valve, you reflect, come back, reflect again, and you have perfect transmission. And you can also calculate the from here wavelength, and what you are going to find is lambda over 2 is equal to 2a over n. Every time your de Broglie wavelength matches a multiple of this valve, you have perfect transmission. And that was exactly what we had for particle in a box. Okay? Any questions? So by using this solution, we can also look at the other geometries. And let me give these as an exercise. And if you want, you can sketch these and look at them. So these are all wells. What you can do, okay, here's, by the way, because we solved it, this is the solution. You can just use what we did here for all these exercises. But you need to keep track of signs and exercise. Generalize or modify solutions to fit in rectangular barrier And rectangular barrier means not this well, but something like this. And now you need to think about the energy too. So your energy can be here, below the barrier. Your energy can be above the barrier. Okay? So these two cases. But this solution is almost correct. You just need to, what fancy people call, you need to analytically continue this solution to this domain. So what you need to do is, first you need to take V naught to minus V naught. And let me write the results and you can compare. So this one, so if your E is less than V naught, so this red line, in this case, classically the particle should bounce, right? There is no way particle can go classically, but if you do the quantum mechanical calculation, the only difference is going to be this sign is going to be sign hyperbolic. And this 1 plus epsilon is going to be 1 minus epsilon. And here you are going to have 1 minus epsilon. Good? So 1 minus epsilon, epsilon, sign hyperbolic, gamma. And if you do E bigger than V naught, the previous solution is exactly intact. And what this means is like tunneling through a barrier at high energies is same as tunneling through a well, right? Even if the energy is lower, you still do exactly the same thing. So this one is, let me look at this. So this is E minus 1. So this is E minus 1. And let me, okay, I'll take 1 minute to sketch this and then we can go. So I want to take this guy and I want to define an if, and this if is this thing is less than 1. So this is the barrier tunneling. If I have the barrier tunneling, this thing is sign hyperbolic. This one is 1 minus epsilon. This one is 1 minus epsilon. And if epsilon is not bigger, less than 1, yes? Oh, yes, yes, thank you. Yes, I think. And the other one is exactly like this. So this one is epsilon minus 1. So this one is exactly as before, sign, this is epsilon minus 1. I think this should be correct. And now, okay, this also works. You can see first small barrier, right? You have this barrier tunneling region, but let me increase it a little bit more. Okay, this one. I think maybe something like that. Okay, this is what we call the tunneling region. So this is tunneling. Right, this is purely quantum mechanical. There is no classical analog. And it says that even if your energy is below the barrier, you can see there is like non-zero probability to tunnel, right? This is 1, somewhere over here 1. And you can see there's like small but non-zero probability tunnel. And once you go over the barrier, this red line, you start to transmit, but these resonances are still there. Even if your barrier is like this, you kind of have this trace of particle in a box, because your energy resonates with the well and you have perfect transmission in these points. Good? Any questions? All right, so we are done with this chapter. I appreciate your patience. Thank you. I'll see you next time.